The major thing in decision maths and this sort of maths that we're looking at the moment, it's a very powerful technique. It can be used in lots of different sorts of problems. What they're looking at here is this network. Okay, you haven't got to see all the numbers in that moment, but that is a directed network. And they're saying one problem could be they're all distances in miles. Find the shortest route from A to E. How would you go about doing that at the moment? Use one of those horrible things from last year. Yeah, which one? Dijkstra. Yeah, okay. And what are you trying to do in that problem? What sort of problem is it? It's a minimization problem. Okay. So that network there could be a minimization problem. That's fair enough. Okay, next. Each weight represents the weight limit of vehicles in tons that can travel on that section of road. What is the heaviest vehicle that can travel from A to E? Is that one we've done so far?
No.
It's not one we've done so far. What are you trying to look at? What are you trying to do there when you're looking for the route?
Find the smallest maximum.
Right, Jack, can you say that again?
Find the smallest maximum.
You're trying to find the smallest maximum. That's what Jack is saying. Is that correct? We're trying to find the heaviest vehicle that travels from A to E. Okay. What did you say, Jack? It was a
smallest maximum.
Smallest maximum. Or is it the maximum minimum? Right. Which one is it?
Smallest maximum.
Well, what's important? What's important is the lowest number on the route, isn't it?
Yeah.
So what are you trying to make that lowest number as big as possible? Okay. So yeah, it's what's called a maxi-min problem, where you're trying to maximise the minimum value on the route. So that's a maxi-min problem, which you haven't come across yet. Number 3. The weights represent profits in thousands of pounds which can be made from carrying cargo en route from A to E. Find the maximum profit. So what are you trying to do there? Maximise, minimise, minimax, maximin? Maximising. Okay. 4. The weights represent the times in hours needed to walk between campsites. Find a route from A to E which keeps the longest stretch to a minimum.
No, minimising the maximum.
That's a mini-max problem. That is where you're trying to minimise the worst part of your journey, if you're a walker. That's a mini-max problem. Number 5. The weights represent activity durations in days. Find a critical path and the time necessary for completion of the entire project. What's that? Are you looking at minimising when you go critical path?
We're trying to find just the most the day.
Critical path, the homework you've just done. What are you looking for? It's not actually, no.
It's the longest time.
You're looking for the longest time. What's take the longest time, which you cannot reduce. Okay. So networks can show all sorts of different scenarios. Some are minimising, some are maximising, some are mini-maxing, and some are maxi-minning. And so far you've seen different techniques for some of them. What we're going to do now is look at a general method called dynamic programming, which can do all of these things in a network. Richard Bellman, 1950, so again a modern area of maths. Okay, and we're going to see this as we go through.